Now we'll look at a slightly different derivation of the Navier-Stokes equations. First, we'll see that a flow can be represented mathematically through a continuous transformation of the deformation of three-dimensional Euclidean space within itself. And we'll parameterize this space by a parameter t, which represents time. There'll be a fixed coordinate system, which we'll see as a Cartesian, and x1, x2, and x3 representing the three directions x, y, and z. And we'll denote a particular position by position vector x. We'll parameterize this position of a particular particle, which we'll call P, or fluid parcel, which will move through the fluid from time t0, which is the initial time, to some other time. And it could be seen as being, in a sense, going into negative or positive time from some position time of 0. X will be determined through capital X as a new position and time t through these particular functions which we want to find and understand, the vector and component respectively, from the new time to the old time, t0. Now, if capital X is fixed and time varies through a path, then the particle could be specified through some mathematical relations in physics. For a fixed time t, this particular equation should determine a particular transform of a region occupied by a fluid into a new position at time t. We'll assume that this parameterization is continuous and that we can invert it, and we'll assume that the inverse exists. So we can write capital X as capital X function of little x in t, and also the components. We'll assume that xi and cap xi are sufficiently smooth and they're differentiable. From the particular condition that the transformation can possess a differential inverse, we can then define the Jacobian in equation 117. Capital J is the Jacobian, and of course it's a function of capital X and t, which might be written as the determinant of partial xi partial cap xj, which gives us a tensor. Here, as normal, the Jacobian will be defined as a positive value greater than 0 and less than infinity. The material coordinate of this particular particle, x, will be its initial position, which is where we're now going to define the material derivative. That's where the name comes from. The spatial coordinates x will be referred to as the position or place of the particular particle, or fluid parcel. Because of the transformation, we can define for x and cap x the hydrodynamic variables, and they'll be expressed in terms of the material coordinates. Here in equation 118, we'll say f of xt, that some hydrodynamic variable, will be a function of x cap xt t, which we can write as capital F xt at position x at time t. So, for example, we can write the velocity u at time t of a particular particle at cap x through this particular definition, which will be little u of xt, which will be equal to u xt, which is the ordinary derivative of x, with x being xt as previously defined. Cap x is the parameter which represents a particular fixed particle, and this is the particular reason we can use the ordinary derivative. If we have a velocity field u of xt, we can determine the principal transformation, solving the ODE, or ordinary differential equation, in 120. d dt of x will be therefore u of xt. Now we can write d dt of f xt and partial t of little f xt. F and cap f are related. So we can write ordinary derivative of f xt is the ordinary derivative of f xt, which will be, upon the substitution, partial f partial xi dx dt plus partial f partial t. We now have a general formula that's really the material or total derivative. The ordinary derivative of cap f is the material derivative of f of xt. So note the capital D's here once again. The material derivative is now defined as, for that particular fluid variable, d dt of f is partial f partial t plus u nabla f, and we'll call this the material derivative.